Welcome back to another exciting episode of Dave Does Math from Home. We are still talking about section 2.2, which is like extra interesting things about functions. And in part 2 of our videos on section 2.2, we are talking very specifically about difference quotients, which are pretty tricky to look at, but once you get used to them, you'll become pretty comfortable with them. A difference quotient I'm going to talk for a little while about what they are before I talk about how to do them, because understanding what they are is an important part of understanding calculus, which hopefully we will see you in a year or so. The difference quotient is f of x plus h minus f of x all divided by h, which looks like kind of a mess. But it's not as bad as it looks, I promise. It's called the difference quotient because it has a difference and is a quotient. So there's difference quotient is basically just a fancy way of saying there's subtraction and division. So that's why it's called that. What it means is it is secretly a way of expressing the slope of something. And it doesn't look at all like slope, but give me a moment to explain this, and hopefully we'll see the connection between this and slope. Slope, we know, looks like y2 minus y1 over x2 minus x1. So if we have something like this and it's some sort of a slope situation, then we can look at let's say we have a function. I want to talk about f of x equals x squared plus 2. X squared plus 2 looks like this. So, oh wow, I'm really bad at drawing this accurately right now. I'm trying to go fast. Okay, x squared plus 2 looks like this. There's a parabola that hits through this point, 0, 2. Let's say I am interested in the slope of the line. Wow, I'm really bad at drawing this. I'm trying to get these things to line up, and they're not lining up. Okay. Sure. We'll pretend this is a good graph of x squared plus 2. So here's 0, 2. Here's 3, 11. And sometimes in math, when we're analyzing a function, we will be very interested in what kind of slope the straight line through these 2 points gives you. So normally we would just plug it into the slope formula like this. We know our y2 is 11. We know our y1 is 2. Our x1 or our x2 is 3. Our y2 is 0. Or our x1 is 0. So this will give us 9 over 3, which is 3. So the slope of this particular line is 3 that cuts through these 2 points on the function. And that's all well and good. This is the same slope formula we've been using for years. The problem is going to come in when we decide that we want to look at, instead of slope as it is defined between 2 points, we might someday want to look at what happens if we define the slope at 1 point, or instead of foregrounding the fact that there are 2 points here, we're going to foreground the idea of 1 point and a distance away from that point. So instead of x1s and y1s and x2s and y2s, imagine for a moment if x1 was the point we were really interested in. Let's just call that x, because that's the point that we're curious about. instead of x2 being a second point, I want to write this in terms of x. So I'm just going to call it x plus h, and we'll say h is a distance away. Distance from x. So instead of having 0, 2, and 3, 11 be like the 2 points that we're interested in, what happens between these 2 points, we can say, I'm interested in what happens at this point, x equals 0, and I'm willing to go some distance away from this, say 3 units away. y1 in this situation is what happens when I evaluate the function at my point x, and y2 in this situation is what happens when I evaluate my function at the point x plus h. So if you try to shift the idea of slope away from these are the values of my 2 points, and you try to shift it towards the idea of here's 1 point and some distance away from that, and here are the y values that come from those 2 positions, the point we care about and some distance away. If you do all of this and then try to write the slope formula, your slope formula is going to be y2, which is f of x plus h, minus y1, which is f of x, all divided by x2 is x plus h, x1 is just x. And if you do this, the x's on the bottom cancel. I'll leave you with an f of x plus h minus f of x all over h, which is the difference quotient. It is exactly the same as a slope. We just changed the symbols around a little bit. Instead of x2s and y1s, x2s and y2s and everything, we're using an x and an x plus h, and functions evaluated at that point. That's the goal. Like I said, looks like a mess, not actually that bad, secretly just a slope in disguise. So that's what it means, and we're going to use it a lot in calculus when we get there. For now, we're just going to practice looking at what happens when we do the difference quotients for certain functions. So I'm going to give us some functions, and we can find their difference quotients. I'm trying to keep this square here because that's where all the glare is. I don't want to write over glare, then it becomes unreadable. So let's take a function. Let's start with a pretty straightforward looking function. We'll start with f of x equals 3x plus 17. I think this was part of our piecewise thing a moment ago, but that's fine. This is a good function. If I want to find the difference quotient for this function, I would start by writing the difference quotient sort of formula. F of x plus h minus f of x all over h. Every single time I do a difference quotient, I start by writing this out. And I would encourage you to do the same. Always start with this. Then we sort of plug the function into this piece. We know what f of x plus h is, because we can do that. F of something is 3 times something plus 17. This is what we were talking about in section 2.1. To evaluate a function at something weird, just write it with an empty set of parentheses, or an empty set of parentheses for each time x appears in the function, and then put stuff into those parentheses. So this piece is going to be 3 times x plus h plus 17. That's me writing this function with x plus h in the parentheses instead of an x. That's this bit. I'm going to switch to a different color. Minus f of x is going to look like minus, the use of big brackets here is really nice, 3x plus 17. And then it's all still divided by h. We'll use a different color for that as well. Okay. So this is the step where you sort of plug the function into the difference quotient. And usually we're plugging things into functions, so it's a little weird. We have a difference quotient which does things with f's and x plus h's and things. So we need to plug our function into that, and this is the result. From here, we need to do some simplification, which we know how to do. We've been messing around with polynomials and expressions this whole time. We can mess around with this expression. We need to distribute this 3, and we need to distribute this minus sign. So this is, after you've sort of plugged in your function, the next step is always a lot of distribution. So we'll have 3x plus 3h plus 17. This piece on the back end should end up giving you I'm going to keep writing this in red. This should give us a minus 3x minus 17. The bottom, I'll go back to black for the bottom. It's all still over h. I wanted to keep writing this in red because once you have finished the distribute everything step, the next step is a lot of things should cancel. Because this kind of looks like a mess right now. We have a weird rational thing with 5 pieces on the top, but this cleans up really nice. 3x and 3x cancel. Positive 17 and negative 17 also cancel. There are, at this step in difference quotients, there are 2 things that I do every time to check to make sure that I'm doing this correct and not making silly mistakes. The 2 checks are everything from the back end should cancel, which is why I left it in red for now. Everything that originally came from this f of x piece, all of those pieces should disappear. And they do. We get a negative 3x, that disappears. We get a negative 17, that disappears. We're good. All of those pieces canceled. So that's check number 1. The second check we should do is everything that's left on top should have an h in it. And again, it does. We have a 3h. That's the only thing left on top, and it has an h in it, and we're good. Now that the only thing left on top has h in it, we can actually cancel this h from the bottom. So the difference quotient of this function is 3, which hopefully doesn't surprise anyone, because I spent the first 10 minutes of this video talking about how difference quotients were slopes, and then I started us with a linear equation. We know what the slope is. The slope is 3, the intercept is 17. We could have said that the slope was 3 just by glancing at this. It's very clear that the slope is 3. Now we know for sure that the difference quotient is also 3. There's a few steps involved to get there, but it works. So I'm going to do another difference quotient, starting with a slightly more interesting function, so that you have another example of how to do this and what it looks like. I'm going to go straight to f of x equals x squared minus 2x minus 8. I want a difference quotient for this thing. So once again, I always start the difference quotients by just writing out what the whole difference quotient is. It is f of x plus h minus f of x all divided by h. Once I have this thing written down, I will plug in the function into this thing. So my function takes an x and squares it, and then subtracts 2 of those things, and then subtracts an 8. Into each of these set of parentheses, I need to plug an x plus h. This is f of x plus h. I'm going to switch colors again, so that I have minus f of x in red. Minus f of x, we're going to do x squared minus 2x minus 8. I'm just going to copy f of x as originally written into brackets over here. So that's the step where I plug in my function. Next step is a lot of distribution, and you have to be very careful about this. This distribution step involves FOIL. You can't just say it's x squared plus h squared. That's missing a huge part of this. We have to FOIL this guy. So this is going to be x squared plus 2xh plus h squared. That's what happens when we FOIL this guy. This 2 needs to distribute, so this will be minus 2x minus 2h. The negative 8 can just hang out. And then this negative sign needs to distribute as well. So I'm going to subtract x squared. I'm going to add 2x, and I'm going to add 8. Oh, and this is all over h. I forgot. Okay, it's all still over h. So this is the distribution step finished. And once we have the distribution step finished, that's when we start asking what cancels. And again, there's 2 checks that we should go by here. Everything on the back end should cancel. Everything that came from f of x, which is all the things that I have written in red. All of those pieces should cancel. And once they do, everything that's left over should have an h in it. So let's see if that happens. We've got an x squared and an x squared. We've got a 2x and a 2x. And I've got, I'll use box for that, I've got an 8 and an 8. So, I was right. Everything here canceled. And everything that's left has an h in it. So I'm going to rewrite those pieces. 2xh plus h squared minus 2h all over h. This is the part where we cancel the h from the bottom. But before I do that, I'm going to factor an h out of the top so I can just cancel that 1h with a 1h. So because everything on top has an h in it, I can factor out an h, and then I'm left with 2x plus h minus 2, all divided by h. And then the h's cancel, and this thing becomes 2x plus h minus 2. This is the difference quotient for this parabola. And again, we're not going to be using these much right now. We'll start using these a lot in calculus. For now, we're not really using them. I just want to get you some exposure to what these things look like so that when you end up in calculus, you have a very clear idea of how to do this. But if we were going to use it right now, it would be to find slopes of things. So sort of like we did in the graph that I drew at the start of this video, I was saying if you want to find the slope on this parabola between 0, 2 and 3, 11, we could just use the slope formula, y2 minus y1 over x2 minus x1. This gives us a bit of a shortcut. So if you're looking at this parabola right here, which I think does something like this, if you wanted to find the slope between x equals -1 and x equals 0, you could say x equals -1 and h is +1, because again, h is just the distance away from the first point that you're using. So this thing would tell you that slope very easily between those 2 points. -2 minus 2 is -4, plus h is 1, that's 1. So that slope would give us an m of -3. I don't even need to know what the y values are here. So that's the utility of this. Again, we're not going to really be utilizing these in class. I'm just showing you this so that you can have some idea of what this is used for elsewhere. In our class, the use of this is just, I want you to have seen it so that when we start doing them in calculus, you have seen them before. Seeing these for the first time ever in calculus is probably a bad point. That's why we're doing them. And we'll talk more about the slopes then when we get to calc. But this is difference quotients. That's going to wrap up section 2.2 for us. I hope that was relatively clear. Good luck on the homework. I'll see you in class.